I think we can start now. So welcome. I am very happy how many participants are online with us today. My name is Victoria and I am your host today. So before we start, I'll give you just a few remarks for your information. Please feel free to type in any questions that come up during the webinar in our questions box. You should see it. We will answer a few questions at the end of the webinar, and if there are too many, we will get back to you by mail. If there are any technical problems, please don't worry. This webinar is being recorded for you, so you will automatically receive a recording of the webinar within the next days by email. Well, now I would like to introduce you to our today's speaker. Praveen graduated with his Bachelor of Technology and has more than 20 years of experience in thermal analysis. He has been part of the NETZSCH analyzing and testing family for over 5 years now, and he's an expert in the field of differential scanning calorimetry and thermogravimetry. Today, he will talk about the basics of the DSC method. So welcome, Praveen. We are very happy to have you here today. I will now hand over to you. So enjoy our webinar and have fun. Let's start the presentation.
Thank you, Victoria, for the nice introduction. Ladies and gentlemen, very good afternoon to one and all from NETZSCH, India. I would like to thank each one of you for taking your time and attending this webinar on the basics of differential scanning calorimetry. Before going to the main presentation, I would just like to take some time to cover the overview of our company, few slides on that. So, yeah. So NETZSCH Group and the business unit analyzing and testing. NETZSCH as a company, we are a German company and we have three main business units: analyzing and testing, grinding and dispersing, and pumps and systems. So I am working for the analyzing and testing division, which has the thermal analysis instruments for the determination of the thermophysical properties. And I will go in detail about some of the products what we have in analyzing and testing in the coming slide. But the main topic will be about the differential scanning calorimetry. The second business segment of NETZSCH is the grinding and dispersing division, which basically has some machines for the dry and the wet grinding, which we call as the mixing or the homogenizing of samples, which are mainly used for the pharmaceutical, process industries and the food industries. And the third business segment of NETZSCH is the pumps and systems, which has a range of pumps, industrial pumps, which are customized as per the customer application. Speaking of NETZSCH Group, we were founded in the year 1873 by Mr. Thomas and Christian NETZSCH in a small town of Germany called Selb. Selb is in the Bavaria region of Germany, very much border to Czech Republic. As of now, we are more than 4,000 employees in 36 countries. That shows that NETZSCH is a global company with a worldwide presence. To give a small overview of the business in terms of sales, so in the fiscal year 2020-21, we were somewhere close to 600 million euros. This graph shows a small overview of the turnover of the company with reference to the employees. So as you can see here, from 2017 to 2021, so we had been growing in terms of the sales as well as in terms of the number of employees. About the products and services of NETZSCH analyzing and testing, we cover a wide range of products which caters to a wide range of temperature. As you can see here, from minus 180 degrees up to 2800 degrees Celsius. And that is the USP of NETZSCH. We have solutions that goes for high temperature applications, mainly for the characterization of metals, alloys, ceramics, which are used in the defense sector or space research, wherein you work at a very high temperature applications. But we are not going to discuss about the high temperature. Today we are here to discuss about the low temperature DSC. We have broadly classified our product range of analyzing and testing. The very first one is the thermal analysis, in which we basically do the phase transition studies. Like, we study the phase transitions of a material, mass change of a material. All that is done with a set of equipments like differential scanning calorimetry, thermogrammetric analyzer, simultaneous thermal analyzer. Then we have one segment called for the thermophysical characterization of characterization of the materials, in which we basically determine the thermal conductivity, thermal diffusivity of a material, and the thermal expansion coefficient of a material. So we have some range of equipments to study this particular thermophysical properties in our product line. The third product line what we have is for the analysis of the degradation and the reaction process with regard to temperature, heat dissipation, and the pressure curve. That is basically being used by the process industries for safety and for the thermal runaway test, wherein we have the adiabatic calorimetry. This is very useful kind of instrument for the process industries. These two product segment, what we have, the fire tester and the rheology, this is a pretty new acquisition of NETZSCH. Before 2 years exactly, NETZSCH has acquired two companies. One is a company called Malvern from Germany, which has a range of equipments for fire testing. So determination of the fire behavior of products in the automotive, construction, polymer applications, with reference to some European standards and ISO standards. Then we have one more product line for rheology. So NETZSCH has partnered with Malvern, UK for the rheometer. So in this we have two range of rheometers. One is the rotational rheometer and the second one is the capillary rheometer. So these are basically for determination of the rheological properties of the non-Newtonian liquids from formulation up to the product usage. Okay, fine. So now we will come to our main topic, the topic of today, differential scanning calorimetry, which is also abbreviated as DSC. Before we go into DSC, we need to understand why to do thermal analysis and what is thermal analysis, right? That's a very basic question which is being used for the material characterization. Now, what is thermal analysis? Now, thermal analysis is basically a technique in which we monitor the physical or the chemical properties of a sample when it is exposed to a specific temperature and time. So when it's a temperature program, it can be a heating program, it can be a cooling program, or it can be an isothermal program. So different programs are being used to study the thermal analysis of a specific material. Now, why do we need thermal analysis? As we can do the melting temperature, linear thermal expansion, we can do the decomposition effects, the mass change, thermal stability of a material, phase transformation, purity measurement, the glass transition temperature of a polymer from a solid stage to rubbery stage, the crystallization temperature, which is very important to determine the strength of a material, viscoelastic properties, volumetric expansion, thermal conductivity, and lot. So a lot of things which can be done by using the thermal analysis. And it's one of the most well-known techniques to characterize a material. Now, how do we do it? Okay, so for doing this, we have some methods. So today we are going to discuss about the differential scanning calorimetry. But apart from that, there are some other known methods as per the standards. So one of the very common equipment which is being used for thermal analysis is the thermogravimetry, which is called as the thermogravimetric analyzer. That is for studying the mass change behavior of a material. So by using the TGA, you can study the mass change, the volatile content, the thermal stability, the decomposition. All these parameters you can study by using a thermogravimetric analyzer. NETZSCH also has an equipment called simultaneous thermal analysis, which stands for STA. Now, as the name itself tells, STA, so we can do DSC and TGA in the same instrument. So it becomes very handy from the user point of view, because instead of having two different instruments and two different programs, he can use one equipment in which he can study both the phase transitions of a sample along with the mass change behavior. So from a user point of view, that becomes very handy. We also have got the evolved gas analysis, we call it as the hyphenation, in which the TGA or the STA can be coupled with a set of equipments like a mass spectrometer, an FTIR, or a GCMS. So we call this study technique as the evolved gas studies, in which the gases coming out of the TGA is taken to a transfer line to a mass spectrometer or to a GCMS for further analysis. We also have some equipments, as I mentioned, like LFA, which is called as a laser flash analyzer for the thermal diffusivity and thermal conductivity and specific heat measurement of a solid material based on the laser method. Thermoreflectance are basically for the thin films analysis. When we go to the nano thickness and the pico thickness range of thin films, this is a pretty well-known technique who are doing research in the field of thin films. Then we have some solutions for the insulating materials, like the heat flow meter, guarded hot plate, for testing the thermal conductivity of foams or insulating materials. Some equipments for the refractories, mainly for the studying the heat modulus of rupture and creep-in compression. Then we also have some set of equipments for studying dynamic mechanical properties of polymer composites, like for soft polymers, as well as for rubber, for tire industries, wherein you speak about very high force DMA. So we have high force DMA also being used by various rubber industries and tire industries. Okay, coming to the agenda. So the agenda of my talk today is divided into three. As you can see here, theory and the measuring principle. Second will be the instrumentation. And third, in which I will go through few examples, some application examples, mainly in the polymer field. So measuring and principle. So what is DST? Okay, so DST is a method which is recognized. It's an international standard method as per ISO and ASTM. As you can see here, the ISO 11357 and the ASTM 474. So what this technique does? This technique basically what it does is that it measures the difference in the heat flow between a sample and a reference material. Now I will show the schematic of DSC in the coming slide, but just for your understanding, it is nothing but it's a heat flow rate. You measure the heat flow rate in the sample. And how do you do it? You basically compare with a reference material which is always empty, a crucible. Now DSC equipment provides a qualitative and quantitative information about heat flow into the sample, which is endothermic, and heat flowing out of the sample, which is the exothermic process. So melting normally is an endothermic process, as you know very well, and then we can also study the crystallization behavior of material at different temperature, and also the changes in the specific heat capacity, the CP of a material. Now, primarily for polymers, these phase transitions are very important, because by studying the phase transitions, you can understand the properties of the polymer. Example, whether it's a pure polymer or there are some additives in the polymer and other factors, environmental factors. So all these factors can be studied easily by using a differential scanning calorimetry, and that's why this technique is very useful for polymer, mainly for the polymer applications. The DSC is based, the NETZSCH DSC is based upon the heat flux DSC. Now, as I mentioned to you, the definition is same. The temperature difference caused by the difference in the heat flow to the sample and the reference is measured. There is also one more method which is called as the power compensation technique. In a heat flux DSC, what we are showing here, we have only one furnace, Whereas in the case of a power compensation DSC, we have two different furnaces. So in one furnace, you will be having the sample, and the second furnace, you will be having the reference. So that's the basic difference between a heat flux DSC and a power compensation DSC. But the heat flux DSC provides more sensitivity of the DSC signal as compared to the power compensation DSC. Okay, so thermal characteristics that can be detected by using a DSC, like we can, as I told you, the melting temperature, which is one of the most critical parameter which we want to characterize for any kind of polymer, the heat of fusion. We also study the crystallization temperature, the behavior, the glass transition, which is called as a TG of a sample, polymer sample. We also do the OIT studies, which I will show you in the coming slide, in which basically you study the stability of a material, mainly for the the telecom industries. I'll show you a slide on that in the coming slides. Degree of crystallinity. Then we have the cross-linking reactions, degree of curing, and specific heat capacity. These are some of the characteristics that can be detected by using a DSC. Applications and the materials are not limited, but the maximum application for a DSC characterization, material characterization goes for the polymers. Then we have some other materials like metals, ceramics, inorganic, organic. Example for metals, we do have a separate product segment, which is nothing but a high temperature DSC, which can go up to 2000 degrees, mainly for the metals and the alloys. Application point of view, mainly for research, for the material development, for the quality control, for the failure analysis, and also to look into the process development. So these are some of the application areas of the DSC. This is the schematic of our DSC, which is based upon the heat flow principle. As I mentioned on the right, as you can see here, we have a furnace which is made up of silver. It's a very compact furnace, and then we have a measuring cell. The measuring cell, it comprises of a sample section and a reference. So both the reference and the sample are within the same furnace, within the same cell. And this sample and the reference, it will have the crucibles. Now we call as the crucibles, but which some people also call as the sample pan. So here we will call it as a crucible. So for DSC, internationally, aluminum crucibles are used for the test and for the experiments. So we have the sample crucible made up of aluminum, which is the lid is pierced, and then we have the sample which goes inside the sample aluminum here. And the reference also has an aluminum crucible, but this crucible will be always empty. And then we have thermocouple, individual thermocouples for both the sample as well as for the reference. Here we have these both reference and sample are sitting on the same common plate. The plate is common for both the sample and the reference, as you can see here. And then we have a flow of the purge gas. Now the purge gas is a gas that flows into the sample. Now the purge gas is usually the inert gas, which is nitrogen. Nitrogen gas is being used. Also we can use other gas for your experiments, even the air. So we can use a range of gas for purging. So in fact, we have a mass flow controller in our instrument, in which you can select two different gases for purging. Example, gas 1 of some concentration, and then you switch on to the gas 2. So that is also possible with our instrument. So you can have a selection of two gases for purge. and then the protective gas which goes around the furnace, and the protective gas is for the nitrogen. It's a nitrogen. As you can see here, as I mentioned, so we have one furnace for heating as well as for cooling, and it's a controlled heating and cooling program. So two fans on the one sensor plate, one reference and the sample, and the heat flow is measured in milliwatt per milligram. Now different transitions what we can measure in the sample is the glass transition, the melting, the crystallization when we heat the sample, or recrystallization when we cool the sample. So we call supercooling, in which we study the recrystallization effect of a polymer, relaxation, curing, and oxidation studies. Okay, this is a typical DSC signal melting. Now we have the electronics. Now if you see the above graph here, this is showing us the electric potential of the thermocouple. Okay, and the x-axis is the time scale. So this we are basically representing how the melting effect happens, how the electronics converts the electronic signal into the DSC value, which we say in the millivolt per milligram. Now, how it happens is that we have shown the green line which resembles the reference signal, and the red line which resembles the sample signal. So you have a reference crucible which is empty, and the sample compartment which has a specific material into that of certain weight, like say 10 milligram or 20 milligram of the sample. Now what happens, initially there is no effect. Both sample as well as the reference signal go line by line same, and suddenly we see an effect here. There's a small effect here. So what happens is that this is called as there's an energy. The energy is getting into the sample, and until it reaches the equilibrium. So it reaches equilibrium point here, and then from here it goes up, and it goes and touches and meets the reference signal. Okay, now this is basically we are assembling the melting behavior. The same if we show it here in terms of area here, as you can see here. So now the software or the computer, it performs the mathematics, okay, and it gets here an area which is here, as you can see, this and this. So it resembles an area which is nothing but as the heat of the reaction, or we call as the heat of the transformation. And this area we measure in joules per gram. Okay, this peak area which we can see in our application also, we will show that area in joules per gram. And this is a typical peak what we can see in our diagram here. We have a sharp peak here which shows an endothermic effect here. Okay, so the DSC principle, as I told you, we have a sample as well as a reference, a sample and reference, and we measure the difference in the temperature of the sample and the reference, and the difference in the heat flow. Coming to the instrumentation part, next we have a broad range of DSCs which meets the requirement for low temperature as well as for high temperature applications. So here, when we speak of low temperature, we have got a couple of instruments which goes from sub-ambient temperature range, the cryo range, say from minus 180 degrees up to 700 degrees. And then we have a range of equipment for the high temperature DSC, mainly for characterization of metals, alloys, ceramics. We have a set of different furnaces which are being used for different temperatures, for low temperature as well as for the high temperature applications. The other product line what we have for DSC is a high pressure DSC. This is a DSC cell which fits into an autoclave, okay, and we perform the DSC studies on this set of equipment at a very high pressure. We say like 150 bar pressure is what we are going to study the pressure for this particular DSC, from vacuum to 150 bar. We have one more feature of our DSC which is called as the UV curing. So what happens is that we expose the sample. So here, as you can see in this here, we have an external UV source here. So by using an external UV source, we superimpose the UV light to the sample, and we see the transitions, the effects of a UV light on the sample behavior. In a normal atmospheric behavior, the sample will behave in a different way, whereas when we expose the sample to a UV light, the sample properties will change, and that are the studies what we can do by connecting the DSC to an external UV source here. So the equipment what we have here for low temperature, the DSC214 polymer, which is here, DSC series here, and the DSC204 F1 Phoenix, and all these are the low temperature DSC. Well, the instrument, there is no control or a switch button on the instrument panel. Absolutely no. The instrument is completely controlled by using a software. Okay, so we have a Proteus software, okay, which can be installed either on a tablet, it can be used on a touchscreen monitor, it can be used on a desktop monitor or a laptop, and it is compatible with the Windows 10 operating system. Okay. These are some of the key features of our DSC, like for all kind of polymers, because broadly, as you know, the polymers we can divide into two categories: the thermoplastics and the thermosets, right? And so basically, what we have it here, we have the hardware part and the software. So what is more important in any DSC is the reproducibility of the results, the reproducibility and the repeatability, and that's what we get with our system. So we get an optimized thermal system, and we use a concave pan. Okay, concave pan, what we use is basically a concave pan. It's a concave pan structure, okay, so that it will be in good contact with the this sensor, okay, because it's very highly recommended that the pan should have a good conductivity and should have a good thermal contact with the sensor. So because of that, we have a specific design of the pan, a concave pan called as a concave pan. It's a very time saving, because why it is time saving? Because in this technique we have a very high heating and cooling rate. Ideally for differential scanning calorimetry, the heating rate is 20 degree per minute or 10 degree per minute, ideally, okay. But for certain experiments, depending upon the sample, we can even program for very high heating as well as for the high cooling. So it's a controlled heating and controlled cooling what we do with our DSC. So the furnace what we have is a very low mass arena furnace. It's a very compact instrument, as I shown in the previous slide, with a very low mass furnace. The interfaces, as I told, we have a software, Windows based, and we have the smart mode software, okay, which means you can use it for different kind of interface like the tablet, or we have some export mode software for some comprehensive settings. Depending upon the usability, these are some of the software tools what we have. I would like to highlight on some of the tools in the coming slide, like the auto evaluation. What is auto evaluation? Identify, which is basically to identify the unknown polymers. So it's basically a database, a smart cooling. Then we also have the auto calibration. Then we have some predefined methods, which is there in the software. Coming to the specifications of our DSC, the temperature range, as you can see here, it's from -170 to 600 degrees. The heating and the cooling rate is variable. As I told, it's a controlled heating and controlled cooling from 0.001 K per minute to 500 K per minute. And the DSC resolution, because this is a very critical parameter for a differential scanning calorimetry. So the DSC resolution for our polymer is 0.1 microwatts. Now, how do we achieve this temperature? The temperature, sub-ambient temperature, the cryo temperature. So how do we achieve that temperature? So we have got the different cooling systems. So here we have a liquid nitrogen cooling system which goes from -170 to 600. So you can do the sample analysis from -170 to 600 in a single run. If due to some limitations, some of the labs they have some specific limitations of not having liquid nitrogen in the lab. So for those kind of options, we have an intracooler. Intracooler is nothing but a chiller. It's a dedicated chiller which can be connected to our differential scanning calorimetry. So we have two different kind of intracooler, which is a -70 intracooler and a -40 intracooler. So the two selections of intracoolers depending upon the customer temperature range and application, the type of the intracooler can be selected. And the advantage of our heat flux DSC, this model, is that you can connect the liquid nitrogen cooling system as well as the intracooler simultaneously. So when I say simultaneously, it means so we have two ports on the rear of the instrument. So you can connect the LNT cooling system as well as the chiller. So you can select from the software which cooling system you need for your test. Either you want LN2 or you want to go for a chiller. Sensitivity is 3.8 microvolt per milliwatt. This we are doing by indium. So indium is normally a reference material for calibration. We use the metallic standard for calibration, which I will show you in the coming slide about the indium. The time constant by using the indium sample, it is 0.8 plus 0.1. This is some of the software features which I told you: smart mode, expert mode, auto calibration. We also have some advanced softwares. Like we have developed our own kinetic software, thermokinetics, for studying the thermal degradation behavior, lifetime behavior of a material under specific environmental conditions. So all that can be studied by using a kinetic software, which is designed by NETZSCH IT software team. Automatic sample changer, this is very handy basically when you are into quality control, because not for research, because research you don't have more samples, so obviously it's not recommended for research applications. But yes, for quality control labs, we do have an option of using an automatic sample changer, which I will show you in the coming slide. Okay. Auto evaluation. Now this is a very useful tool of our software. Now what happens is that before the software were being used, okay, the user will sit and analyze the graph. Like he will look at the various transitions, he will refer to some manuals and books and find out what are these different transitions that are happening in my graph here. But by using the auto evaluation software, which is supplied with our DSC, you can do the rapid evaluation. Just with one mouse click, you can get the auto evaluation results here. Like at what temperature is my glass transition? What is the onset temperature? What is end set temperature? What is the delta CP value? What are the different graphs, different peaks we are getting it here? Example, the melting peak we are getting here, the complex melting peak here. What is the peak area with reference to temperature and the DSC? So all this we can do just with one mouse click, and that's why this becomes a very handy tool for most of the industries, especially for QC, and also very handy for research. So it's reliable and it's user independent. So even experienced user can use it as an independent second opinion or for verification. And there's no extra training because it's just one mouse click, you can do the auto evaluation. So obviously it saves a lot of time and money for the user. The another software tool which is very useful for analyzing the DSC curves is the Identify. So we have this tool here in our software. So when you click on this, so what happens is that Identify software is nothing but a library. Normally, like how you have got the library in a FTIR database, so same set of library we have in our DSC called as the Identify software. Now, Identify software basically for identifying the unknown polymers based on the melting point of material. Now, example, what we see here is that the Identify software searches for the similar results stored in the polymer library providing the instantaneous interpretation of the measurement at hand. So with the identified package, it is possible to carry out one-on-one comparison with the individual curves or the literature data from the selected libraries, or to check whether a particular curve belongs to a certain class. Okay, so this example for any kind of polymer, you can use that. You can do the quality control test, example whether the polymer is pass or fail in terms of quality control. And this, we have a library, but as a customer you can also user define. So this is flexible in that sense. So we already have a set of library, but you can also put your own user defined programs in this particular library. Okay, we specified about a point called the OIT. Now, OIT studies is very important. It is basically an ASTM method, ASTM 3895 method, which are mainly used for testing of the tubes, cables, mainly for telecom industries. For them, OIT studies is one of the most critical tests that is being done for polymers. Now, what is OIT? It is basically for studying the stability. Okay, now what happens is that you basically do the heating of a sample under a specific atmosphere. Normally it is nitrogen atmosphere, and then we switch to the oxygen atmosphere. So what we study is that the time taken by the sample before oxidation. Before oxidation, the time taken, it is called as the oxidation induction time. Now this OIT is directly proportional to the relative stability of the material at a specific temperature. So that's why OIT is one of the most important tests which is being used by certain industries, as I mentioned, telecom industries. Yeah. Okay. So for any equipment, for any analytical equipment, or for thermal equipment, obviously calibration is one of the most important parameter. You need to have some reference, you need to have some standards for calibration, so you are sure that your results are within the values. Now what happens is that we do the enthalpy as well as the temperature calibration. So for enthalpy and temperature calibration, we have got some metal standards, and traditionally, in most of the cases, indium is being used to study the melting behavior. The melting point is 156.6 degrees Celsius. We also use advantane, which is melting of 270. We also provide some metals like tin, zinc, and bismuth, the melting point of 271.5. So we provide this particular standards with our low temperature DSC for the enthalpy and temperature calibration. But this is not limited. For customers who want to do the specific heat measurement, we also provide some specific heat standard. We provide the sapphire standard for the specific heat measurement. Okay, so as I mentioned, this is one of our DSC model. Okay, and this is the automatic sample changer. So we can put 20 different samples. Now these samples can be of different type. It can be of different volume, it can be of different environment, it can be of different crucibles. Okay, so say like sample 1, you can use, example, it's a PET sample. Okay, and sample 2, example, it's a blend sample. Okay, so you can program your sample, say sample 1, heating rate 10 degree per minute, cooling rate 10 degree per minute, atmosphere nitrogen. Same way you can select it for sample 2, sample 3, and so on. So what is an advantage of that is that you get a very high sample throughput. So example, if you are a QC lab, and then if on a weekend, you can put your samples, program it, and when you come back on the first day of your week, you see your samples being analyzed and the results are ready for all your samples. So that becomes a very handy tool for that. Okay, as I mentioned about the cooling accessories, so for -170 to 600 degrees, we have this electric cooling system. This is a Deva tank. So this is portable Deva tank, which can be moved across the lab. It's a 60-liter tank, as you can see here, with the controller and the regulator, and it can be connected by this hose pipe directly with our DSC. Then we have this two different kind of chillers, or the intra coolers we call it as. So depending upon the temperature, it can be from -40 to 600 degrees, or we have another intracooler which goes from -70 to 600 degrees. So depending upon the cooling requirement, the customer can identify his requirement to select which kind of cooling accessories has to be brought. This is the same set of specifications for another model. We also have an option in which if the customer wants to do the studies at room temperature to 600, he doesn't want to do any studies sub-ambient. For that, we provide a small compressor. So again, that is also possible with our instrument. We provide a small compressor to do the studies from room temperature to 600 degrees. But yes, it takes a lot of time when you use a compressed air, because the cooling time is high to bring the furnace temperature back to the room temperature. Okay, coming to the crucibles and the sealing press. Okay, because as I mentioned in my slide, that we use the aluminum crucible which has to be sealed, and it's a pierced lid. Okay, so normally we use the aluminum crucibles. It's a standard aluminum crucibles being used for most of the polymers. Okay, but again, for different applications, we have different crucibles. Now, this is specific kind of aluminum crucibles for solid fat index and for the OIT determination. So we have this sample crucible and the lid, okay, which is a pierced lid, and we crimp it because basically we have to crimp this crucible, and for crimping the crucible we have the sealing press or the crimping tool. So it's a manual lever, you can just press it easily, it's very handy, and the crucible is sealed and it is ready for a test on the DSC. We also have some copper crucibles for the OIT measurement. As I mentioned, there are a range of crucibles what we have apart from the standard aluminum crucibles. Like we have got alumina, platinum, rhodium, silver, zirconia, graphite, depending upon the temperature range, because graphite crucibles are mainly used for high temperature applications, which is being used for our high temperature DSC. But for low temperature DSC standard, most of the experiments it's being performed with the aluminum crucible. Okay, coming to the sample preparation. Now, for any DSC sample, there is no specific sample preparation required. Unlike other techniques like gas chromatography, wherein you have to digest the sample, a lot of sample preparation is required and time is required to prepare the sample. DSC is very handy and very easy in that aspect. So we provide a sample cutter, so you can take a portion, you can just cut it. Okay, and that portion of the sample you can load. Usually we take ideally 10 milligram or 20 milligram of the sample in our sample pan. But if the sample is not homogeneous, then in that case we take a more amount of sample. But ideally for most of the polymer studies, if you go with 10 milligram or 20 milligram of the sample. We also have got the sample preparation kit, as I have shown it here. So it comes along with the instrument. Okay, and we also have got the medium and the high pressure crucibles. Okay, for specific kind of samples like epoxy resins and different kind of samples, we need to do the study of the sample at very high pressure. So we have a stainless steel crucibles which is crimped again with using very special kind of tool, just called for the high pressure crucibles. So again, for specific experiments, we also provide some high pressure and the medium pressure crucibles up to 100 bar. Okay, now we'll come to the application, some of the application examples of the DSC, which will be mainly focusing on the polymer part. Okay, so this is an application which we are showing for a polyethylene tetrafluoride, the PET. Okay, so as you know very well, like depending upon the sample type, okay, whether the sample is a semi-crystalline or whether the sample is an amorphous sample, it shows different behavior. Okay, now mostly for the amorphous samples, we are more interested in studying the glass transition behavior of the of the amorphous material. But for the PET, what we are studying here, as you can see now, this is the sample, the PET sample, and the crucible what we have is the aluminium crucible with the pierced lid. And the sample mass what we use it is 8.43 milligram, like 10 milligram of the sample, and the heating rate is 10 degree per minute. So what we do is that we do the study, say like from room temperature up to 250 or 300 degrees, and we study the different behavior of the polymer of this PET material. Like initially what the point what we get here, the small one, this is the glass transition temperature. So the glass transition is happening at almost 75 degrees over here, and then this peak is the cold crystallization peak of the sample, in which the temperature is almost close to 138 degrees, and we can also get the peak area, which is the software gives you the peak area, which is almost like minus 34.96 joule per grams. It's always shown in joule per gram, the heat, the area. And then the big peak where we get here, which is the melting peak. The melting peak, in which we have the area of 39.5 joule per gram, and the peak temperature, which is the 251.2 degrees, which is the melting temperature what we get it for this polymer. Now, this is the first heating what we have done here. Okay. Ideally, we can also do the second heating. So what we do is that we heat the sample, we study the glass transition, the cold crystallization behavior, the melting, and then we cool down. So when we cool down at a specific heating rate, say like 10 degree per minute, and we study the recrystallization behavior of the sample. Now, why first heating and second heating? See, because what happens is that when you do the first heating of a sample, okay, the first heating of a sample contains important information about the processing history, the storage condition of the sample. Okay, so that data you can get with the help of the first heating. Whereas when you do the cooling, okay, and do the second heating run for the same sample, you get additional information of the behavior of the material. So ideally, it is a good practice to do the first heating as well as the second heating of the sample. The second example what we are showing here is the glass transition of an amorphous ABS sample here, acrylonitrile butadiene styrene copolymer, and in this we are basically interested for studying only the glass transition, okay, being an amorphous sample. Okay, so we have taken a sample of almost 13 milligram. Again, the crucible is aluminium, the aluminium pierced lid. Atmosphere is nitrogen. Heating rate is again 10 degree per minute. A very important point, sorry, which I forgot to miss out, is that here in our graph, the exothermal behavior, the exotherm is shown downwards and the endotherm is shown in the upward direction. But we have a choice to select whether you can make it upward or downward, because exothermal is normally the melting, and the endothermal is the melting, and the exo is the crystallization behavior. So we can select the direction of the exothermic or endothermic by the software itself. Now in this particular amorphous ABS sample, as you can see, we have this program, say like from minus 125 up to 160 degrees, and we have a heating rate. We have a heating at 10 degree per minute, and here we get we are getting one a transition, a phase transition here, which is small glass transition. We have the onset at minus 84, and we can also get the delta CP value for this particular transition. And the second transition, what we get the glass transition is for the polystyrene step, which is we are getting at almost like 110 degrees with a delta CP value of 0.276. And the third one, the glass transition which we are getting is for the polyacrylonitrile step, which is almost close to 125 degrees. So again, for the amorphous sample also, mainly for the studying the glass transition behavior, we can very much use the DSC. Coming to the final application, we are studying about elastomers. Now here we are studying the test on the fluoroelastomer FKM, and here we are studying the glass transition and the curing behavior of the fluoroelastomer. The sample, as we have shown, it's an FKM sample. So it's a crucible, which is aluminum crucible. We have a sample of close to mass of close to 20 milligram and a heating rate of 10 degrees per minute. Now, in this, what will happen is that we have a temperature scale on the x-axis and the TSC milliwatt per milligram on the y-axis. You can see it. Now, when we heat the sample, okay, so we basically perform the first heating and the second heating to study the curing behavior of this particular material. Okay, so at the first heating, we find the glass transition around minus 20 degrees. And then we again go on, we continue heating the sample, and there we find a small effect which is here, which might be a small additive to this sample. And then we go on heating, and here we get the big one, the broad peak, which is nothing but the curing. Which is the curing, okay? So normally for rubbers, we also call it as the vulcanization behavior of the rubber. So this is the complete curing which has happened. Now, again, when we want to go back and we go to the second heating, okay, to study the glass transition. Now, what we can see in the second heating, which is the green one, you can see that there is no more curing. So the curing is gone here. Okay, so what we can see is that also there is a small shift in the glass transition. As you can see, in the first heating, the glass transition was happening at close to minus 19, whereas in the case of the second heating, the glass transition is happening at close to minus 17 degrees, the glass transition, and there is no more curing which is happening in the second heating. So these are some of the applications which we'd like to show you for the DSC. Okay, so that is end of my webinar. So first of all, thank you very much for attending this webinar. I'm very thankful to each one of you, and I hope that you got some information about the differential scanning calorimetry, the principle, and might be a small idea on the operation and some of the applications of the DSC. So we have some time left. So what we can do is that if you have questions, you can please put your questions in the questions section, and